Good evening. Happy Wednesday. Yeah, happy Wednesday. Let's take a look what we found yesterday in mathematics, just out of curiosity. Ah, yeah, out of curiosity. Ah, yeah. Yeah. Well, the thing is this, in mathematics, you cannot quite predict, like, let's say there's some mathematicians come up with some kind of theory, right? You never know whether that theory will be proven useful in the future or not. Okay, many times it happens in mathematics. Some mathematicians that develop a theory like group theory, for example, just out of curiosity, out of its beauty, right? But later on, it finds sometimes those purely theoretical mathematics finds some handsome application in the real world setting. Okay, that happens a lot in the history of mathematics. Okay, so yeah, who knows? Maybe this will have some application in the future. Uh, we don't quite need these two lines, so let's get erase these two lines. Oh, I'm sorry. It happens. Sorry about that. Automatic adjustment to brightness. Sorry about that. We don't need these two last lines. Let's erase it, okay? And we're gonna expand this, plugging in K to see what it looks like. Alright. Out of curiosity, that's all. That's a hobby. Very easy mathematics, nothing fancy. No calculus, just algebra. Right? Algebra time. Alright. Ah. So happy, I'm sorry. Happy Thursday. Happy Thursday, everybody. Yeah. Happy Thursday. And, how was your day? I hope you have had a very good one. We're gonna expand the sigma, okay? So, zero, k is zero is one, one. So, k is zero, so that becomes one, right? Right? When k is one, one. Mm. In case two, Uh, Probably it's easier to just leave it as it is, huh? Like 4 to the K, yeah, 2K. In case 2, 4. Okay, 0, 1, 2, K3. Ooh. Okay, okay. Ah, it is kind of counterintuitive, okay? So it is counterintuitive. Um, it's not very obvious that this series is an infinite series and it converges and as n goes to infinity, okay? Um, n goes to infinity. Would it? Is it obvious that it converges? Actually, it is obvious, huh? Yeah, yeah. It should converge. Why? N goes to infinity, and you have n squared and 4 squared and to the 6 at the bottom level. So yeah, they all go to 0. What the only thing that's left is 1. It is trivial. Okay, okay, okay. It is trivial. All right. Well, okay. I'm sorry. Maybe this equation isn't that useful. All right. So we expanded this sigma, and it's very obvious that it converts to 1. Okay. All right. So maybe it's not very useful formula, but hey, it is true, and although it may not be very useful, but it's true, and it's fun. Intellectual entertainment, so it serves the purpose. So yeah, yeah, yeah. Okay, we'll take 5 minutes break. All right, and then we'll have some more fun with mathematics. Something like raw algebra. Okay, so or some cyclic sequence, periodic sequence. Okay, yeah, just for fun. Okay, so all right, let's take 5 minutes break. Interesting. Yeah, so we had enough fun with this. So Okay. Well, my house is still warming up, but I needed to bring in the fresh oxygen. That's why I opened the window. Um, okay. Whiteboard hunting. Uh, let's see. Oh, this one's heavy. Yeah, we'll use this guy. Somebody please invent electronic whiteboard, okay? It's just big tablet. Maybe there's already one. Just big tablet PC so that we can save this without erasing it. Uh, yeah. Anyways. But it's all tape recorded. And will be published in the Google YouTube, so yeah. Okay. Okay. Uh, so periodic sequence, integer sequence. It doesn't have to be integer. It could be any number. By the way, one comment about uh, yeah, I read some kind of article about that Ukrainian American brothers. They uh so the article mentioned um was that Gero Cantor, all right? I think Gero Cantor is a little bit exaggerated figure, okay, overrated figure perhaps, okay. He's not founder of set theory. He kind of popularized set theory. The founder of set theory, that's more like George Boole or Peano in Italy, George Boole in England, and some others. Okay, so Mr. Cantor didn't really contribute too much to set theory. Okay, well, he kind of popularized set theory, and he's good. He made some contribution like diagonal method. It's very smart method, proving technique. Diagonal method. That was very smart, but he yeah. So he says he proved that there are more transcendental numbers than algebraic numbers, and Kronecker rejected that proof. Okay, so how about me? Well, I don't know what that proof is about. I don't want to read it even. Okay, so whether that proof is correct or not, I don't know. And but that kind of makes sense actually. Why? Well, transcendental number it's more or less random, right? Uh, but algebraic number Uh, it's more like algebraic numbers are like more, there's more cosmos, more rules, more pattern. Kinda, okay. Of course, square root of 2, yeah, you don't get to see any pattern in the digits, like 1.414, blah, 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 right? Um, Square root of 3, yeah, 1.732, blah, 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 right? Yeah, you don't quite get to see any pattern there either, right? So, um, yeah. But I'm not sure if his proof is correct or not. Why? Because Mr. Gero Cantor, I don't think he got he asked some good questions like cardinality, infinite set, and blah, blah, blah. But some of his answers were wrong. Okay. Um, like he defined unit infinity as some set is that can be done with one-to-one correspondence with the integer or something like that, and that's very wrong definition. Okay. Um, okay. So for the rest of this year, we'll just do some mathematics without writing any papers. Why? Because we want to take a break from all those paper writing. Okay. So yeah. So happy holidays. Okay. So I kind of feel healthy nowadays because I reduce smoking cigarettes. I reduce cigarette smoking. Maybe that's why. I don't know. Maybe I eat better nowadays. Yeah, I kind of eat. I don't diet. Well, I eat a lot of fruits and vegetables. Okay. Every now and then, I also eat like chicken gizzards, fried chicken wings. Okay. I guess that's perhaps fine. Yeah. Like once a week. But yeah, fruits and vegetables. Yeah, I eat them. Fruits I eat in the morning as a breakfast. Okay. That seems to be a very healthy habit. Healthy diet. I feel healthier. Cigarettes, I smoke less cigarettes. Okay, so fruit. I mean vegetables. Yeah, yeah, I eat when I cook stuff. Yeah, I put vegetables in there. So maybe that's why I feel healthier. Okay, so I mean, you watch K-pop, right? I mean, if not you, but some people watch K-pop music video, and yeah, handsome Korean boys. I get it. Okay, but when it comes to their music and dancing, just not my cup of tea. Okay. Now I'm Korean American, ethnically I'm 100% Korean, so I'm 42 years old. Okay, let's say I'm pretty. Huh? Let's just pretend I'm pretty Korean Asian boy doing mathematics. Maybe it's better than watching those K-pop videos, bunch of Korean pretty boys. At least we are doing some intellectual brain exercise with this mathematics. Okay, so okay, periodic sequence. Okay, let's say you have an, okay, and n one. Well, we have to start from zero. Okay, zero, one, two, three, 4, 5, 6, 7. Okay, and some random number like let's say 5, 2, 7, 5, 2, 7, blah blah blah. Okay, so how do we express this periodic sequence in terms of n? That's the question. Okay? I give you like 5 minutes. Okay? Let's regroup. All right. I give you 5 minutes. So express an in terms of function of n in one line. Okay. Uh, hint. Well, there are many ways you can do this. I guess I don't know, but we're gonna use row algebra. Okay, and that's how I would go about it. Okay, row is just remainder operator. Okay, for example, 15 row 2 1 because divide 15 with 2. Divide 15 by 2. What's the remainder? 1. Okay, that's what it means. Row. Okay. All right, we'll take 5 minutes. If you want, yeah, express this infinite sequence of integer. It doesn't have to be integer, okay? And with finite expression of a row algebra. Okay? If you want to. Okay? We'll take 5 minutes. Right. Okay. I give you more time. I'm gonna take selfie. Yeah, I guess I carry good energy level today, so Yeah. Okay. Uh, some vodka. Yeah. I give you more time, okay? Using raw algebra, why don't you express this? No, closed form formula, okay? Closed form formula. Maybe it's already known using some different symbols like modulo, but modulo, yeah, that notation probably invented by Gauss, Friedrich Gauss, German mathematician. But it's kind of bulky. It's awkward to write. Like parent, open parent, mod, close parent. Mm. In computer programming language, they use like ampersand. Not ampersand, but percentage sign. Some program languages use that. Okay, instead of row, but we use row for remainder. Okay. So period of this cyclic sequence is 3, right? We've done this before. Okay, it's a review. Okay, so it's like if n row 3. Well, first draft. Okay, n row 3. If it is equal to 0, then 5. That's it. Yeah, it's Iverson bracket. The we rather call it Boolean hybrid because that's what it is. Okay, it's hybridization of between Boolean algebra and regular algebra. Okay, so okay, it's like Kronecker delta. Okay, so if this is true, then it's one. The whole thing. Okay, the Boolean term. If this term is false, then it returns 0. Okay, so yeah. Now that we have plus plus, yeah, we can compact it using sigma, right? Sigma notation. I give you 2 minutes to express this guy in terms of sigma. Okay, I want to drink. Today's Wednesday, right? Did I say Happy Thursday? I'm sorry. Happy Wednesday. It's not Thursday yet. Yeah. Happy pre Thursday. This is good. Alaskan blueberry vodka. So good. I have some Alaskan crowberry vodka over there. This is really, really good. Yeah, this one I picked earlier this year, 3 months ago, about when I went to hiking. 1 hour north of here in the mountain. Crowberry. Pretty Asian boy doing mathematics. But K-pop guys, they dye their hair, they like have lipsticks. I'm like, why? What? Why? Why? Why dye your hair? Why put lipstick? You're a guy. Why? What's it with lipsticks, man? Uh, some Koreans are very weird. Okay. Yeah, I'm very weird Korean myself, but at least I don't put lipstick on my lips. Come on. What's that for, huh? Huh? Red lipstick on boys' lips? What's that about? Yeah, whatever. Oh boy. Alright, let's do it. Sigma k from 0 to 2 uh, n row k, no, n row 3 is equal to k multiplied by a k, right? 0, 1, 2, 5 to 7, okay? So, in general, alright? Let's generalize this even further. Yeah, an in general, sigma k from 0 to period p minus 1 n row p is equal to k multiplied by ak. Okay, that's our formula for generic periodic sequence of numbers. It doesn't even have to be a number actually. It could be alphabet or symbols. All right, because if it repeats itself, yeah, then this is the generic formula for it. All right, so yeah, p is a constant. K is a sigma variable, so it cancels out. We after we expand, only thing left is n. So n is the variable, right? Function of n, right? So good. We did this like year ago, right? It's a review. Yeah. We'll take 5 minutes break, okay? And, Let me take a picture of this. Okay. Pretty Asian boy doing mathematics in Google YouTube. In Alaska, drinking vodka, taking his selfies. Oh, oh boy. There's nothing wrong with that. And some people may say, "Oh, what a pity! What a pitiable, pitiful, pathetic." But I don't think so. We're having fun, staying out of trouble, so there's nothing wrong with it. We are not doing anything illegal or immoral. Some intellectual entertainment, which is great. Right? Okay, we'll take 5 minutes. Okay. Alright. So in this, let's take a break from mathematics. Okay, so in this version of humanology, there are many out there, but in this brand of humanology, uh, we have emphasized exercise and diet. Okay, so uh, the because PT it can stand for two different things: physical therapy or physical training. In the army, I can only speak for army. Okay, because I never been to other branches. Okay, U.S. Army. Okay, so yeah, PT means physical training. It's preventative measure, as opposed to physical therapy. That's like after you got injured or got out of surgery, that's physical therapy, right? And it costs money. But physical training is more preventative measure. That's better. Okay. So, and because the kind of exercise we do here is about balancing. You stand on one foot, you jump, kick, punch, martial arts, push ups, sit ups, pull ups, the whole body concept, right? Your legs, your arms. What about people who cannot exercise? Disabled people. Well, guess what? They can still do exercise. Okay, so yeah, it doesn't matter what your body type is, okay, or physical limitation. Yeah, I mean, if you're injured in your legs, yeah, you can exercise with your arm, your neck, right? Yeah, or even you can exercise with your facial muscle, like, right? Yeah, or eyeball, right? Yeah, exercise. Okay, it is great. Okay, so uh, okay, so the article I read about this Chudnovsky, Bratia Chudnovsky, okay, Chudnovsky brothers, okay. They talk about randomness, okay. So the guy in New Yorker magazine, the editor, contributor of that magazine, yeah, very good writer, and obviously he knows a lot about science. Maybe he majored in some science. Yeah, I can tell. Yeah, smart guy. But yeah, I can kind of see his knowledge about mathematics is not too deep because from the way he writes, yeah, I can tell. Yeah, he does not know mathematics in depth. Okay, I can kind of tell. Okay, maybe no major mathematics undergrad level. Yeah, I can can't tell that he doesn't have the depth of knowledge in mathematics. I could tell. Okay, most likely he knows less mathematics than I do. Okay, so but he's a good writer. He understands more mathematics than average people, I guess. Okay, so but I can kind of tell. Yeah, uh he does not know mathematics in depth. Right, more than average people, but still. I could kind of tell the way he write. Okay, but he brought some good points. Okay, so like he was talking about random numbers. What's the randomness? Okay, yeah, yeah. If there are truly random infinite sequence of alphabets, then you can find some Shakespeare's poem in there somewhere. Very good creative thinking. Yeah, good thinking. Yeah, good thinker. Yeah, mathematically speaking. Yeah. So let's explore that because there was very inspiring article and it was very long article. Okay, so but yeah, it was very interesting. Good concepts there. So okay, well, let's explore the possibility. Very inspiring. So let's grab another whiteboard and. All right. Whew. Okay. So we can construct an infinite number, right? A string, infinite string, all right? Well, it could be base 10 or base 2. We'll just use base 2. Why? Because it's simpler. It could be base 1, like 0, 0, 0, 0, 0, 0. But that's not very interesting. Okay, so we'll use base 2 because it's a lot simpler. Because principle is the same thing. Okay, so a number, infinite base 2 number. Okay, so we call it x. Okay, 0, 1. Okay, then 0, 0, 0, 1, 1, 0, 1, 1, then 0, 0, 0. Blah blah blah. Okay, so yeah, just base 2. Okay, in alphabet, yeah, use A through Z. The word consisting of only one character in alphabet, right? And then next group will be all the words consisting of two alphabets, like AA, AB, AC, AD. At the end, ZZ. Okay, something like that. Okay, so yeah, we can construct that kind of infinite number. So yeah, this study of pi by this Chudnovsky brothers, yeah, it does have some significance. Okay, so yeah, that article pointed out that. So the writer of that article, smart guy. Okay, in New York Magazine, regular contributor. He write about science in general. Okay, yeah, I guess he's smart guy who know a lot of science. Okay, so, okay, yeah. Maybe it was not entirely his idea. Maybe he interviewed these Chudnovsky brothers many times. Maybe it was Chudnovsky brothers' idea. Okay, sure, whatever. Okay, but at least he was able to understand what they were saying. So, co-contributor of this wonderful concepts. Okay, yeah, good investigative journalism, scientifically speaking. Okay, yeah, it was a very good article. It was written in back in 1992. That was like back in 1992. I was a middle school student in Seoul, South Korea, 1992. Okay, so I feel the writer of this New Yorker magazine was older than me. Still is, like, right? So okay, all right. What else? Uh, cardinality. Okay, let's revisit the. It's a review, all right? We're not doing anything brand new. Cardinality, all right? Because the way Mr. Well, Herr Georg Cantor defined this unit infinity, I have to disagree with the way he defined it. Okay, so we redefine cardinality, the unit infinity. Okay, all right. We're not going to use some fancy Hebrew alphabet like Aleph. Okay, no, it's just too difficult to learn those foreign characters. Okay, so instead of Aleph, we use Alpha. Aleph, like ALF. LF, Alpha, LF, right? Probably same word origin, like character origin. Okay, so in Middle East, okay, you have Aleph, you have Hebrew, Arabic, Greek. Yeah, same Middle East, North Africa, Southern Europe, nearby, right? So proximity. So they are related languages. Let's take 5 minutes break. Okay, so they will do this infinity algebra. Okay, we can call it alpha algebra, infinity algebra. Okay, we'll do that. Okay. Right. Let's take a break. All right. All right. So alpha algebra, infinity algebra. Okay, you need infinity. We'll just call it alpha. Okay, and we can call it omega. Like Judeo-Christian tradition, alpha and omega. That's how God characterized himself. Maybe Jesus, beginning and end. Yeah, in humanology, we have different interpretation of that verse, alpha and omega. It's like, yeah, very first and very last, like servant leadership, right? I ran into that term when I was looking for this Korean word. What is servant in Korean? Because I forgot. Okay, I lost a lot of vocabulary, Korean vocabulary. So when I talk to my parents in my cell phone on the weekend, I'm like fumbling around this memory space in my head between my 2 years. How's this between my 2 years? Okay. What's that Korean word? That happens. Yeah. The only time I speak English is when I speak to my parents or some Korean friends in America. Okay. Some Korean relatives in America. Okay. So that's the only time I speak Korean. Okay. So, okay. So Jesus said the ones who want to be the first should be the last. The servant leadership, right? Yeah. So in the previous paper I wrote, yeah, African American, their ancestors, we don't want to characterize them as slaves. That's disrespectful. How about servant leaders? I wrote that, okay, previous paper. It's a good paper, okay. It's published online in the internet, online database is there, all right. So, Humanology One, this book, yeah, online database, okay, so it's all out there. So nowadays we're just having fun with mathematics year end for the rest of the year. We have like what 2 weeks left in year 2020. 2020 has been very good year for us. Okay, for others not so much, but for us, yeah, Vision 2020. Okay, we cranked out 5 papers, collected them, make into one book, 277 pages. Everything is published online databases. Okay, so it's been very good year for us. Okay, vision for the future. All these papers and book, right? We published online for free so that anybody can download PDF versions thereof. Yeah, it's been fantastic year for us. Okay. Okay. Alpha algebra. Okay, so alpha. All right. You set of natural numbers, right? Infinite set. Okay, and the cardinality of set natural numbers. Okay, that's the definition of alpha. Just the unit infinity. Okay. Now, next level. Set of rational numbers. Okay. Q. So Q is like set of rational numbers. What is the rational number? Yeah, this article about Chudinovsky brothers, he did talk about this too. Okay, so very inspiring. Okay, so Rational number q is x. Yeah, Trojan set notation. Okay, x is equal to a over b, where a belong to, well, we exclude zero. Okay, because for simplicity. Okay, where, well, we use semicolon. Okay, a comma b, they both belongs to some integer n. Oh, I mean, let's do this right. Okay, so semicolon. A can be, okay, integer set I is like dot 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 minus 2 comma minus 1 comma 0 comma 1 comma 2 comma dot dot dot. Okay, so A is a member of integer, comma B is a member of integer. Integer set minus 0 set. Okay, there we go. I mean, because in convention, traditional mathematics convention, you don't divide by zero, but in our humanological mathematics, we do sometimes divide by zero. Okay, so, yeah, we'll deal with that later. Okay, just part of the infinity algebra. Okay, so yeah, we are just reviewing what we did in the past, year ago, 2 years ago, 3 years ago. Okay, so okay, so can we express cardinality of Q in terms of alpha? Okay, so that's our thing. Okay, so Mr. Gero Cantor asked the right question, but he got it wrong. All right, so but he asked the right question. That's good contribution, huge contribution. All right, dealing with infinity. Okay, but he got it wrong. All right, so we want to correct his errors. Okay, we want to finish what he started like 100 years ago. Okay, Mr. Gero Cantor. He asked the right question, but he got the answer wrong. Mr. Albert Einstein. Yeah, he has the right question, but he got the answer wrong. We corrected Mr. Albert Einstein, and we also corrected Mr. Cantor, right? We're just reviewing his concepts. Okay, so we did this way back, all right, years ago. Before we tackle Q, rational number, okay, we'll tackle I. Okay, so cardinality I. How many numbers are there? Yeah, what is that? In terms of alpha, it's 2 alpha. Okay, it's and well, 2 alpha plus 1. But yeah, absorption rule, yeah, plus 1, it gets absorbed to 2 alpha, so this is 2 alpha. Okay, so 1, yeah, is 0. Okay, so n is positive integers. Okay, but I integers, it has 0 and negative integers. Okay, so 2 alpha plus 1. In infinity algebra, yeah, plus constant, it gets absorbed to infinity. Okay. So my next question to you: how do you express Q in terms of some function of alpha? Okay. Okay. So that's my question to you. Okay. So and we'll take 5 minutes break and we'll do this together. Okay. Yeah. Express cardinality. What's the cardinality? Number of elements in this set. Alright? Number of elements in this set. That's cardinality or absolute value of this set. Number of members, elements in this set. Okay, so it's very relativistic. Okay, so if we define alpha as the number of positive integers, okay, then relativistically speaking, how would you express the number of members in this set of rational numbers? Fractions, okay? We did this like 2 years ago, year ago, okay? So it's just a review, right? So yeah, fill in the blank if you want to. You don't have to, okay? We'll do this talk after 5 minutes, okay? We'll take 5 minutes break. So, all right. Take more time if you want to, okay? Okay. Okay. Yeah, we're gonna have to grab another whiteboard, alright? So it's a little bit involved, alright? So we need brand new whiteboard, okay? So whiteboard hunting. Alright. This guy. Alright. Yeah. Cardinality of rational number expressed with alpha, which is cardinality of natural numbers, positive integers. Okay, so why is it so difficult to erase this thing? Oh man. Ay, it's dry. Alaska winter very dry, right? Ghost of numbers, zombie numbers, right? Apparitions of the past. Give it some stability in this tripod, easel. I encourage you to be ambidextrous, right? Learn to write, learn to use chopsticks, left hand, right hand. Okay, why? You need both hands to give a break to the other hand. Alright. Otherwise, you may get injured. Alright. So you should use both hands. Yeah, when you brush your teeth, use left hand, right hand, okay, so that you don't have any injury, okay. Okay, very important. Be ambidextrous. Okay. So, all right. It's getting too hot. I'm gonna turn off the heater. Ugh. Okay. So, rational numbers. Okay, between one and zero, zero and one. Okay, you have zero and one. How many rational numbers are there? Okay. Well, it's like this. Okay, you have one over two. So rational number is just fraction. Okay. And you have 1 over 3, 1 over 4, okay? And 1 over 5, blah, 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 okay? That's the one half of that, okay? So, it's like, this is alpha. So you have alpha here. Like 1, 2, well, alpha minus 1, okay? So, which is alpha, okay? So, in denominator, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the infinity, okay? So that's the cardinality of natural number, okay? Minus 1, because you start with 2, not 1, okay? So, okay. So that's the first half, lower half of this cardinality, okay? And the second half, it should be symmetric, right? So you have, this is alpha, okay? So second half, Yeah, you have alpha too. Okay, so oh, what are some examples? Yeah, let's think about it. All right, so I mean, here you have I don't know. I mean, you have two over three. That's for sure, right? Yeah, two over three, and somewhere you have like three over four, and somewhere you have two over five. This is smaller than two over three, right? Yeah, two over five, three over two, three over five. Well, that should occur before two or three. I'm sorry. Whatever. Okay. Somewhere here you have three over five, right? And four over five. Whatever. Okay. Is it more than alpha? Maybe. Huh? Maybe. But that's kind of strange. We explore that. Okay. Yeah. We didn't quite get into too much detail of this. Okay. So we'll think about it. Okay. We got time. Maybe this is more than alpha. Okay. So let's put a question mark in here. Okay. So rational number. Well, you have 1 over 6, but you have 2 over 6, which is, well, 4 over 6. Okay. No, no, no. Let's say you have 1 over 15, and then you have 2 over 15 sometimes, okay, which is less than 1 half, right? And 4 over 115 too, okay, so maybe this is not alpha, okay, yeah, yeah, it's not alpha. Yes. Let's think about this, okay? Yeah, it's always been involved. Okay, cardinality of rational numbers. Okay, it's been a while. Last time we tried this, I'm not sure if we got it right. Maybe I made some errors. Okay, yeah. How many rational numbers are there between zero and one? Right. So yeah. Well, it's like this. Okay. So some x, okay, rational number x is equal to a over b. Right? They are both integers. Okay, b is not zero. All right, and it's just that they are integers, positive integers. Okay, it's just that a is less than b. or equal to whatever. That doesn't matter. It's minor detail, right? So okay. So how many combinations? This combinatorics, okay? I guess this is alpha squared. Alpha squared, okay? So cardinality of Q rational number, I guess this like alpha cube. Why? Because here you have alpha times alpha multiplied by alpha. Okay, so okay. My conjecture is this, okay? Cardinality of Q is equal to 2 alpha cube. Okay. Why? And which is same as uh yeah, whatever. Let's not jump ahead. Okay, so cardinality of integer is 2 alpha, right? Yeah, we know that, right? Yeah. Okay. It's combinatorics, infinite combinatorics, infinity combinatorics. Okay. Yeah, all the possibilities. Okay, so A is a non-negative integer. Okay, 0 plus. Okay, non-negative integer. Okay, which is same as n union 0. Okay, and B belongs to the set of natural number. Okay, we'll define natural number excluding 0. Right, just positive integers. Right, so I plus. Okay, positive integers. Okay, so there's alpha times alpha. Okay, all these different possibilities. That's alpha squared, right? And it's just between 0 and 1. You have 1 to 2, 2 to 3. How many of them? Alpha. Okay. So alpha times alpha, alpha squared, right? Between 0 and 1. And you have alpha of them, so that's why it's alpha triple. I mean, alpha cube, alpha to the third. And that's just positive rational numbers. When we account for negative rational numbers, just twice. Okay, so we got it. Okay, so okay. How about irrational numbers like logarithmic numbers or some root, cubic root, square root? We'll talk about that later, maybe tomorrow. Enough mathematics for today. Okay. Okay. This is publication material. Okay. Because it's different from Gero Cantor's definition of unit infinity cardinality. He used this one-to-one correspondence in function theory. Okay. I think that's very wrong definition. Okay. But he asked the right question though. Okay. But he didn't answer it right. Alright. So it's very relativistic. Okay. Not Einsteinian relativity is all wrong. Galilean Newtonian relativity. Okay. So alright. Okay. Oh, we'll take 5 minutes. Okay. It's heavy, very challenging. Right. Yeah. Let me take a picture of this and then we'll take 5 minutes. Okay. Yeah. Ouch. All right. Let's take 5 minutes. All right. So yeah, let's take a break from all this mathematics. We'll just talk about some mathematics history in narrative. Okay, let's put this behind us. Okay, we'll continue this tomorrow. Yeah, we're doing mathematics. Okay, so having some fun with numbers and symbols, operations, right? Yeah, it's fun. Intellectual entertainment. So good. I mean, if you don't understand this, don't worry about it. It's not important. It's just entertainment's sake. Different kind of entertainment. Okay, so yeah, entertainment industry. What do they do? Yeah, it's all about money, power, fame, sex, violence. How about some intellectual entertainment? Okay, so that's what we do here. Okay? Yeah, brand new kind of entertainment. Right. So back in the days, we are talking about early 1900s. Right. Yeah, Mr. Harold David Hilbert. Okay. Yeah, good mathematician. Okay. Yeah. He had many students. One of them, Wilhelm. I mean, that's German William. Okay. Wilhelm Eckermann. Eckermann function. Okay. So I learned about Eckermann function when I was in Madison, Wisconsin, studying for majoring computer science. Okay. So yeah, complexity theory. Okay, it's big numbers. Okay, very big numbers. All right. So yeah, Eckermann function. Okay. So recursive algorithm, stuff like that. Okay, so Mr. Eckermann, he was a single guy when he was a student of David Hilbert, maybe PhD candidate or maybe postdoctoral research scientist. Okay, so and then he got married. All right, and Mr. Head David Hilbert, he said, "Yeah, you got married, so I'm providing for you. You used to be a single guy. I could provide for you all this research grant in Germany, okay? But you got married, you're gonna have kids. So now I have to provide for not only you, but your wife and children as well. I cannot do that, okay? So he fired him, alright? You are on your own, okay? I cannot provide for your wife and kids, okay? You got married too early, okay? You should have gotten married after you get some professor job so that you don't have to rely on me, depend upon me. I cannot make that much money. I'm just a mathematician. Yeah, Harold David Hilbert. I have to let you go, okay? Because I have other PhD candidates or postdoctorals that I have to support financially, research grants, right? Mathematics does not make that much money, okay? So you're on your own, okay? You have wife, you have children, okay? You have to get another job, okay? Because I cannot provide for your family, right? So Mr. Wilhelm Eckermann, yeah, I think he got a job as a high school teacher. Okay, he got married too early. Okay, that's that's some anecdote in history of mathematics, but he's brilliant mathematician. Eckermann function. Yeah, you have tetheration and you have hyperoperation. Okay, yeah. I thought I was the first to discover it, but it wasn't. Okay. Later on, I learned that it was Mr. Herr Wilhelm Eckermann, okay, and Professor Donald Knuth, not Donald J. Trump, but Donald Knuth, professor in computer science. Okay. Yeah, Knuth's notation or convention, like up arrow, down arrow, whatever. Okay. So later on, I learned that yeah, I was not the first to discover that generalization of plus. your plus multiplication, and then you have power, right? A to the fifth, and then tetraration and hyperoperation. Yeah, it was discovered before I did it. Okay, so that's fine. But we go beyond that. We conduct inverse operation. Okay, so in every level of, yeah, we'll talk about that like tomorrow or week or so. Okay, so we have to talk about it because it's something very important, right? So when you increase the level of operation, plus multiplication, power, tetraration, and fourth, fifth, sixth, seventh, okay. Every time, yeah, you come up with these inverse operators, where it bifurcate. All right. After third degree, so fourth degree plus second degree multiplication, third degree, this power, okay, and it stop being commutative. Like a to the bth is not the same as b to the eighth. So they start to bifurcate in terms of inverse operations. Okay? Plus inverse operation minus. Multiplication, inverse operation, division. But power, it bifurcate. Okay? Root, like square root or cubic root, or logarithm. Alright? Tetrations and fifth, sixth, seventh, yeah, is they have two inverse operations. Okay, and you come up with brand new universe of numbers each time. Two kinds. Okay, it is publication material. Okay, so but Mr. Professor Donald J. Not Donald J. Trump, but Donald Knuth. I don't know what his middle initial is. I don't even know if he has middle name. Okay, so Professor Donald Knuth of Stanford University Computer Science Department. Okay, so I don't think he's an encyclopedic knowledge. Okay, he's very good academic, kind of librarian. Okay, bookkeepers, keepers of knowledge, good teachers. Okay, he learned broadly and then computer science, mathematics. Okay, and then he teach. He's busy. Okay, but we are not that. We are not encyclopedists. Yeah, we have broad knowledge, but we are more interested in discovering brand new knowledge. We are creative, laid back. Okay. So yeah, we didn't go to Harvard, Yale, Stanford. So what? Alright? We want some academic, scholastic independence. Alright? Yeah. So this hyperoperation, inverse hyperoperation, always bifurcate and two inverse operator in each level, each echelon, right? Yeah, each echelon, probably same word origin, right? Come to think about it. So each echelon, each level, each stair, each floor, we have two brand new inverse operations that give birth to two different kinds of numbers in each level, right? So yeah, we talk about that, okay? For the next 2 weeks, okay? It's a little bit involved, okay? Not too much though. Yeah, we need to cover the concept to calculate cardinality of real numbers. Okay, including irrational numbers. Okay, yeah, one step at a time. Okay, so we have time. 2 weeks before this prosperous, propitious, wonderful year of 2020. 2020 vision. Vision for the future and beyond. Yeah, you're blessed. Year 2020 has been very good year for us. Okay. Okay. All right. I'm too drunk to continue. Okay. So I gotta eat. We watch some videos. I'm inclined to watch this V series. Okay. Yeah, I can slow down. Okay, but still, it's okay. So I continue to watch this V series. Right. Alien invasion. The visitors. Okay. Visitor something like John Kenneth or something. Okay. So, okay. All right. Happy holidays. Bye. Thank you. I love you. Thank you.